let's share the PowerPoint. And here we go. They show you a spiral galaxy. I'm not sure which one it is. That's not important. We will go on to Isaac Newton, famous, probably an apocryphal story, not really true, but they show Isaac Newton with a tree and an apple by the side. His apple fell on his head, and it got him thinking about what made it fall. Like I said, probably an apocryphal story. So let's just go on. Newton came up with the Universal Law of Gravitation. Every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The formula that it came up with, gravitational force, is equal to G times the product of the masses, M1 times M2, divided by the separation distance squared. And G, the constant, is 6.674 times 10 to the minus 11 Newton meter squared per kilogram squared. So that's Newton's famous law. The 6.674 times 10 to the minus 11, you don't necessarily have to commit that to memory. You will be using it for homework and tests, so write it down somewhere. You don't necessarily have to memorize it. So let's see, I didn't keep up with my notes. He came up with that law. Well, in 1687, he published his Principia Mathematica, which is the mathematical principles of natural philosophy. This is where he had this law. And in what is the year? In 1798, Sir Henry Cavendish did this experiment that verified Newton's law. And if you look, he's got on this very fine fiber, he's got these masses, these small masses, balanced on either side of this fiber. And then he would bring heavier masses approaching them, and they would be attracted. And the turning, they would turn. You could see that in this case they're turning clockwise if viewed from the top. He could measure the amount of turn, and he verified Newton's law. Now, there was about 100 years later, Philip von Jolly was able to perform other experiments. And for those of you that are listening to this video, you can just write a little paragraph or two, nothing more than a page. I don't want to read a whole bunch of stuff, but if you can just look up Philip, that's Philipp, Philip von Jolly, VON, and then JOLLY. So it's 3 words, Philip von Jolly. Look up Philip von Jolly and look up his experiment, and just do a little write-up on it. It can be handwritten, or if you want to type it up, that's fine. Again, paragraph, 2 paragraphs, maybe a figure that shows what he did. Look up Philip von Jolly. It happened about 100 years later, and he was able to measure the attraction of about a 6 kilogram. I forget what the exact. I'm not. Yeah, but I guess about 6. It's not 6 kilograms. 6,000 kilogram mass. It's about a 1 meter ball that he used in his experiment, and he was able to do some measurements with it. So just give me a write-up, extra credit. Philip von Jolly, his gravitational experiment. All right. Okay, so here's again the gravitational equation. The force of gravitation is equal to G times M1, M2 over R2. So this is consistent with Newton's third law. If you have a force 2, 1, it's equal to, that's the force of 2 by the influence of 1. That's equal to the negative of force 1, 2. Again, here's the equation. Force of gravity is equal to G times M1, M2 divided by R2. This is, and we're going to come across this some more. We'll see it when we come to the force between two uh, charged particles, whether they're positive or negative. We'll see the electric force has it has a different constant. Here the constant is G. It's going to have a KE. And instead of masses, we're going to talk about the charge, coulombs per charge, but there'll still be a 1 over r squared. This is what is called an inverse square law, and we see it quite often in physics. In other words, the square of the distance, it falls off by a square of the distance. So if you have two particles attracting one another, and you double the distance, well, since it's r squared, you've cut the force into 1/4. We're going to have a little quiz later on, and now you know the answer. Okay, this is it in vector form, where r12 is the unit vector in the direction of mass 1 to mass 2. And when you have a large mass like the Earth distribution, you can imagine it as all of that mass being in a single point at the center of mass, located at the center of mass. And you can do that. F of G equals G times the mass of the Earth times some m. You choose an m, and the radius of the Earth squared. Well, I did that. I used a 1 kilogram mass. Well, what is 1 kilogram times 9.8 meters per second squared is equal to 9.8 newtons. Easy calculation. Well, if you do this calculation, you can even add it on to the Von Jolly assignment, more extra points. The force of gravity is equal to G, which is 6.674 times 10 to the minus 11 times the mass of the Earth. I just used the alpha search. I forget what Mathematica has, a Wolfram alpha, I think it's called. I used the Wolfram alpha search. I came up with 5.972 times 10 to the 24 kilograms for the mass of the Earth. And for the radius of the Earth, I use 6.371 times 10 to the 6 meters. So you use those values, 6.674 times 10 to the minus 11, and times 5.972 times 10 to the 24 kilograms times 1 kilogram. Well, of course, the 1 is not going to affect it. And then divided by 6.371 times 10 to the 6 meters squared. I came up with 9.81953, and that's very close to the 9.8 if we just use the gravitational acceleration constant, lowercase g. All right, let's continue on. A planet has 2 moons of equal mass. Moon 1 is in a circular orbit of radius r. Moon 2 is in a circular orbit of radius 2r, so it's twice as far. What is the magnitude of the gravitational force exerted by the planet on Moon 2? Well, since the radius is doubled, and the formula has 1 over or mass 1, mass 2 divided by r squared. Well, if it's 2r squared, that ends up being 4r squared. So it's 1/4 as large as that of Moon 1. And there's the answer, 1/4 as large. And that's going to do it for this section. We'll go on to free fall acceleration and the gravitational force in the next one.